Hello everyone, we are glad to present our work, Coterie, exploiting frame similarity to enable high-quality multiplayer VR on commodity mobile devices. Virtual reality enables highly immersive and interactive experiences to users in the virtual world. It has already been applied to many different areas, for example, entertainment, education, and enterprise or military training. As a result, the global virtual reality market is expected to reach about $33 billion by 2022. In order to support those experiences, VR has very stringent QE requirements. The first one is low motion-to-photon latency, meaning the time needed for users' movement to be fully reflected on display screen should be smaller than 25 milliseconds. The second one is high frame rate, that is FPS, frame per second. It should become larger than or equal to 60. The third one is mobility. VR system should become wireless or untethered to avoid tripping hazard. In today's VR market, there are two types of VR devices, tethered VR system and untethered VR system. Tethered VR system requires to connect to strong PC through HDMI cable. The strong PC renders VR graphics and then transmits VR frames back to those headsets through HDMI cable. Therefore, tethered VR system enables to support high-quality VR. As for untethered VR system, it exploits its own hardware resources to render VR graphics. But because of limited hardware resources, untethered VR system cannot support high-quality VR. In summary, neither tethered system nor untethered system can satisfy three QE requirements together. So we ask the question, can we enable high-quality untethered VR over today's wireless network? It turns out, the prior art has already solved the single-player problem. And our contribution in this work is to enable multiplayer on commodity mobile devices. As our work is built on top of single-player VR design, I will give you a brief review of the existing single-player solution. To begin understanding the challenges of single-player VR design, let's go through two Strawman solutions to single-player VR. The first one is to render completely on the mobile device. The second one is to render on the remote server and then transmit frames to the headset over wireless network like A0211AC, the most common wireless network today. Since it is omnidirectional, users' movement will not affect wireless signals. We tried 3 high-quality games on Pixel 2, and FPS for local rendering is around 24 to 27. The reason is that GPU load is close to 100%. It means high-quality VR exhausts the mobile device resources. For remote rendering, FPS is only 5. Network transmission for single frame is 208 millisecond to 216 millisecond. So remote rendering exhausts the wireless network bandwidth. Since two Strawman solutions fail to support single-player VR, how does prior art enable single-player VR design? Next, I'm going to introduce to you Furion, published in Mobicom 17. If we take a deeper look at those games, here's one example. We can see two monsters walking in the village. The two monsters are actually foreground interactions, FI. Since FI is triggered by humans, it is unpredictable. On the other hand, FI has lower complexity to render, so it has lower rendering workload. The rest of the game, including the houses and the sky and etc. in the game, is background environment BE. BE is fairly predictable, but has higher rendering workload because it has much higher complexity than foreground interaction. Based on those two insights, Furion proposed to decouple foreground interaction from background environment. Foreground interaction is to be rendered on the mobile, while background environment is to be pre-rendered and pre-encoded on the server. Furion's client prefetches the background environment frames from the server during the game. Since it's hard to predict viewports in VR games, Furion deals with panoramic background environment frames, which are 360-degree background environment frames. As for prefetching background environment frames, because virtual world is always discretized, Furion cuts it to grids. Here's one example. The player starts at location 0 at T0, and Furion prefetches panoramic frames for location 1, 2, 3, 4. When the player starts moving from location 0 to location 3 at T1, Furion starts to prefetch for location 5, 6, 7. Since BE frame for location 3 is prefetched and cached locally already, Furion's client starts decoding paradigmic frame for location 3. Meanwhile, Furion starts rendering foreground interaction on the mobile device. In order to satisfy the low motion-to-photon latency constraint, Furion does all those three things in parallel, which also explains why Furion needs to prefetch the background environment frames. Here is the performance comparison among rendering on mobile, rendering on the remote server, and Furion. As shown in the bottom, Furion enables 60 FPS for those three games. GPU load on the mobile side is only 12.9% to 14% because foreground interaction is lightweight. The network transmission for prefetching neighboring background environment frames is about 7.5 millisecond to 9.3 millisecond. In this work, we are focusing on multiplayer VR, because multiplayer VR represents significantly new genre of VR games. The popularity of multiplayer VR games keeps increasing. Study shows 77% of users want more social engagement in VR games. Rec Room reaches over 1 million VR headsets. VR Chat raises $10 million. Those two games are two of the most popular VR games. Meanwhile, Facebook plans to release the social VR called Horizon this year. In order to support high-quality multiplayer VR games, we asked the question, can we simply extend Furion to support multiplayer? However, the answer is no. It turns out two-fold Furion already saturates the network. Here is the topology of Furion. There is a server sitting on the edge, and the mobile device sends prefetching requests to the server, and the server replies the background environment frame back to the client. Two-fold Furion is that we have two clients, and each client simply replicates Furion's client and uses PON, photon unity networking, to synchronize foreground interaction between two players for the next frame. The result shows, for two players, FPS is only 45. The total network bandwidth reaches the maximum wireless bandwidth, around 500 megabits per second, while the network transmission time is doubled. Meanwhile, CPU load on the server side is below 12%, and the GPU load on the client side is around 15%. Therefore, it proves that the network becomes the bottleneck. But why? Why is network the bottleneck? For Furion, network bandwidth requirement equals prefetching frequency times frame size times number of players. As we increase number of players, network bandwidth requirement increases linearly. But frame size cannot be easily reduced further, because Furion has already pre-encoded background environment frames. Now, we only have prefetching frequency left. Can we reduce the frequency of prefetching background environment frames? To answer it, let's first take a look at a short video here which is recorded from one player viewport. Let's see how a player moves in the virtual world. If you pay attention, you will probably notice the key observation here is players always move continuously. Therefore, the background environment frame between location I and location I+1 should be similar. If the background environment frame prefetched for location I can be cached and reused at location I+1, we can save prefetching from the server. Actually, there are two notions of frame similarity in multiplayer VR games. The first one is intra-player frame similarity. Here is one example. The player moves from grid point I to grid point I+1. The similarity of background environment frame should be similar between those two adjacent locations. The second one is interplayer frame similarity. As shown here, the second player stands at grid J. If background environment frames between grid I and grid J are similar, we can reuse them between two players. But how much frame similarity is there exactly? We evaluate night games. We quantify those two similarities using SSIM, a well-acknowledged metric by image processing community. It is used to measure similarity of two frames. SSIM larger than 0.9 means good similarity. Surprisingly, it turns out that for intra-player frame similarity, only 0% to 20% of frames have good similarity, while the best-case interplayer similarity is close to 0%. Our key insight here is Nearby object effect causes really low similarity between two adjacent locations. Nearby objects cause noticeable difference in the rendered frame, even if the player just moves a little. The bottom right here is one example of background environment frames at two close viewpoints. With entire BE, SSIM value is 0.41. After removing nearby objects, SSIM value increases to 0.86.
Understanding this root cause motivated us to design a new multiplayer framework that exposes the frame similarity and drastically reduces prefetching frequency, therefore the network bandwidth requirement. As we learned that nearby objects degrade similarity, the key idea is to segregate the background into two parts and render them separately. Although the virtual world is 3D, but player, here denoted by the star, moves in a 2D space. So we can draw a circle to segregate the background. All objects inside radius R is considered as near B and rest is far B. If near B is rendered on mobile and far B is rendered on the server, then we can get rid of the nearby object effect, which degrades the similarity. This makes prefetching less frequent, which in turn reduces network bandwidth requirement. Now, how we can decide the cutoff radius for segregating near and far background? While deciding, we need to maximize the radius in order to have maximum similarity for far BE frames, while we have to maintain the rendering time of near background on mobile device. We can have a single cutoff radius for the entire game, but it's too coarse-grained. For different location in virtual world, object density is different. From the picture, as you can observe, left location has fewer background objects, hence sparse, while right one is denser with more background objects. Hence, we can customize radius per location, which in turn incurs high overhead. Although the object density can vary in different location of the game world, but it tends to be very uniform within a small region. With this observation, we proposed an adaptive cutoff scheme that drastically reduces the overhead for customizing a radius per location. For more detail of our adaptive cutoff algorithm, refer to our paper. After applying our adaptive cutoff scheme per region, we repeat same measurement study over the 9 VR games. We earlier stated that frames with more than 0.9 SSIM considered to be highly similar. From graph in left, adjacent far BE frame similarity improves from 0 to 20% to 65 to 100%. While graph on right shows base case interplayer similarity improves from 0% to 55 to 100% for 6 outdoor games. With this enhanced similarity for far background, using our adaptive cutoff scheme, we implement 3 versions of cache exploiting different similarity on Viking Village game. Player can either use similar frames from its local cache, intraplayer similarity, or from cache with overhead frames, interplayer similarity, or both. Version 1 exploits the intraplayer similar frames, which provides 80% cache ratio, while in version 3, interplayer similar frame provide nominal benefit on top of version 1. With these key ideas and design primitives learned before, now how easily we can put any VR game into Coterie. First, on server, applying the preprocessing module to our VR game, we get all adaptive cutoff parameters for the game world. With these adaptive cutoff parameters, rendering engine pre-render all possible far background panoramic frames, then H.264 encoder pre-encodes those frames into far BE videos. Our modules frame cache with prefetcher, which performs caching and prefetching frames from server those are not present in local cache. Renderer, which renders the near background and foreground interaction and merges with decoded far BE videos by decoder module. These 3 modules need to be added to the VR game along with Google Daydream SDK and Photon Unity networking module as plugins in Unity game engine. Finally, we can port the resultant APK to any Daydream supported phone, here Pixel 2. Hence, any VR app can be easily ported to our system Coterie. How is this portable Coterie system performs over the state-of-the-art solutions? While performance evaluation of our system, first we ask the question, can we achieve acceptable QoE? Observe the visual quality and FPS metric. We need to run VR for an extended period of time. So how is resource usage? Finally, we verify whether reusing similar frame degrades the QoE through a user study. For performance evaluation, 4 players played the Coterie ported VR game on 4 Pixel 2 phones inside Google Daydream headset with controller. Phones are connected to a wireless AC router which is directly attached to a powerful game server. We ported 3 apps with highest grid point density, Viking Village, CTS Procedural World, and Racing on Pixel 2 phones. Can our system achieve acceptable visual quality? To answer this question, we compare SSIM of frames generated by each scheme with local rendering. Higher the SSIM value, better will be the visual quality, while SSIM greater than 0.9 provides good visual quality. From the table and the picture, we can easily observe our system provides greater than 0.93 SSIM, hence good and acceptable visual quality. What frames per second our Coterie system can provide? As one can clearly observe for the 3 high-quality VR apps, while existing Furion solution extending to multiple players, Furion miserably fails to provide 60 fps, our system Coterie can easily provide 60 fps while supporting 4 players. Now with this acceptable QoE, can we really run our VR system for an extended period of time on mobile device? Here we varied the number of players from single player up to 4 players and show our VR system overhead on mobile device in terms of mobile CPU, GPU and power usage during the gameplay. The graph shows at max only 35% CPU and 63% GPU usage by our Coterie VR system for 4 players, while power draw stays fairly steady at forward. Hence, Coterie incurs acceptable system overhead while supporting 4-player high-resolution VR on mobile devices. As we started with network being the bottleneck, let's find out how much network bandwidth is required. Graph on left shows bandwidth variation for Viking Village for 30 minutes gameplay while varying number of players from 1 to 4. Exchanging foreground interaction with other players incur a very little overhead of 270 kbps. While for background videos, Coterie incurs a maximum of 100 Mbps bandwidth while supporting 4-player high-resolution VR on mobile devices. To check whether adaptively cutting the background and reusing similar frames affects the user QoE or not, we performed a user study. Here 12 participants compared 2 videos, one before segregating near and far B and always using exact frames, and another one for Coterie, and rates their difference. Mostly participants rate the difference either 4 or 5. Hence most of the participants think the difference is either invisible or visible but acceptable. To conclude, in summary of this presentation, simply replicating state-of-the-art single-player Furion system to multiple players fails to support more than one player due to linear increase in network bandwidth. Coterie exploits similarity of background frames from nearby location to reduce the bandwidth needed for prefetching BE frames from the server. Our system Coterie maximally exposes the BE frame similarity by removing the nearby object effect and revisiting how the rendering workload should be split between mobile and edge server. Finally, Coterie can reduce network bandwidth requirement by 10 to 26x while supporting 4-player high-resolution VR apps on Pixel 2 over 802.11ac. Thank you.